In this precalculus algebra video, we're going to define hyperbolas and graph them as well. So first, let's start with the definition. A hyperbola is the set of all points in the plane, the difference of whose distances from two fixed points, called the foci, is a constant. Okay, what does that mean geometrically? Let's take a look. So here I have 2 points in the plane along the x-axis. The first point has coordinates c0, and the second point has coordinates negative c0. These are called the foci. What we're going to do is we're going to graph the set of points such that when you take the distance from the points to the foci and you subtract those two distances, you get a constant. So let's draw on those two line segments. So imagine that we were thinking about that distance right there, and then this distance right here. Let's call the first distance, let's call it D1. Let's call the second distance, the second line segment D2. And so we're going to consider the lengths of those two line segments. Let's call that point, let's give it a name. Let's call it point P with coordinates x, y. So the distance formula says that if you want to know these distances, right, what you do is you first calculate the square root of x. You take this coordinate and you subtract that coordinate, so it's going to be x, take away negative c. That's going to be x plus c, quantity squared. And then you add to it y, take away 0 and square that. That's just y squared. So that's the length of D1, right? So this is D1. And then we're going to subtract from that the length of D2. So that's going to be the square root of, likewise, x take away c squared plus y take away 0 squared. So we're subtracting D1, we're taking the length of D1 and we're subtracting the length of D2, and we're setting that equal to some constant. We're calling that constant 2a, and you'll see why we didn't just call this a, but we're calling it 2a. And the reason is because a is going to have a geometric significance up here. So D1 take away D2 is a constant, okay? And that's what a hyperbola is. It's the set of points for which the difference of those two distances is a constant. So when you go ahead and do that, when you find the set of points that satisfy this equation, the graph ends up looking something like this. Okay, and let's draw on those points now. So this would be the graph of one what's called branch of our hyperbola. Our hyperbola is going to have two branches. So for every point on the hyperbola, so let's take this point for example, if you were to take the distance to the first focus and subtract the distance to the second focus, you would get the constant 2a. That's true for all points on this branch. Now it turns out that to get the second branch, all you have to do is say, hey, well, we don't care if this is positive or negative. In other words, D2 take away D1. In other words, if you let the distance to the second focus be larger than the distance to the first focus, if you let that still be the constant 2a, you'll get the second branch. So the second branch is going to be like this. Let's go ahead and draw that in now. Okay, so here I've drawn in the second branch of the hyperbola. So this branch, the left branch, together with the right branch, those together are the graph of the hyperbola. The hyperbola does not include these lines. Those were just for illustration. So the set of points satisfy this equation. I added a negative 2a in here as well to reflect that we don't care if D1 or D2 is larger. Now it turns out that if you isolate the radicals and then in this equation, if you isolate and then eliminate the radicals one at a time, this equation can be written in the following way. X squared over a squared take away y squared over b squared is equal to 1. So if you look at this and compare it to the graph of the equation of the ellipse, it looks just like the ellipse except for one important difference. And that important difference is that instead of addition in the middle, it's subtraction. Okay, and so in that case, all you have to remember is change addition to subtraction in the middle, and you've got a hyperbola on your hands. Now, in this equation here, a is greater than 0, b is greater than 0, and b is defined similarly to how it was defined in the with the ellipse. In this case, though, b squared is equal to c squared take away a squared. And it turns out that if you look at this equation, you can see that it has x-intercepts but not y-intercepts. I can see that, right? It crosses the x-axis but not the y-axis. And to figure out where it crosses the x-axis, you set y equal to 0, and you can see that x squared over a squared is going to be 1, so x squared is going to be a squared, so x is going to be positive a. So here's one intercept at a0, and then here's another intercept at negative a0. So these are points on the hyperbola. So we call those vertices. So just like with the ellipse. So the vertices are the points positive or negative a, comma, 0. Let me write that a little clearer for you. So positive, negative, a, comma, 0. And the foci are, they are still like they were before. They're positive, negative, c, comma, 0, as they were with the ellipse. We should know, I should mention that the axis connecting the two vertices, so there's like a little line segment connecting those two vertices, that's called the transverse axis. So the transverse axis for this hyperbola, the transverse axis is horizontal. And in a moment we're going to see a case where the transverse axis is vertical. Now what's the length of that transverse axis? Well, from here to here is a. So by symmetry, well, the fact that this is negative a0 means the transverse axis has a length 2a. So it's got length 2a. Now it turns out that you can take this equation, you can isolate y. So if you get the y by itself in this equation right here, you're going to get this. Y equals positive or negative b over a times x multiplied by the square root of 1 take away a squared over x squared. So a few steps from there to there to get the y by itself. Now the reason we do that is because we can notice something when this equation has been written in that form. As x gets really, really large, notice that this is going to 0 because a is fixed and the denominator is getting large. So this whole thing is going to 0. So this is approaching 1 because it's the square root of 1 take away something really small. So what's happening is, as x goes to infinity, the y is getting closer and closer to just this, positive or negative b over a times x. Now that tells us that the hyperbola has what's called a slant asymptote. So it's a line that the the hyperbola gets closer and closer to as x goes to infinity or a negative infinity. And the reason that's important is because we're going to use the asymptote when graphing hyperbolas. Okay, so let's see how it's going to break down. Now that we know what the equation of a hyperbola looks like, what do you do? How do you graph it from beginning to end? And let me show you our strategy on the next page. So you start with something like this, right? X squared over a squared minus y squared over b squared is equal to 1. So the first thing we notice is that the vertices, once you have this, are positive, negative a, comma, 0. Then what we do is we create this little this box, what's called the central box. Central box. And the way you create the central box is you take the b, you on the y coordinate, on the y axis, you go up b, so here's b, and then down b, and I'm doing that because b is below the y, and then you go over a on the x-axis, whatever that number happens to be, and then negative a the other direction, and you create this little grid, this is called the central box right here. It's not on the graph, but it's helpful for graph, it helps you to graph. So right there you've created this little central box. And what we're trying to do with the central box is we're trying to graph the asymptotes y equals positive or negative b over a times x. Now you can graph those lines just separately if you want. You don't have to create the central box, but with this box what you can do is you can draw a line through this corner, and that line will be one asymptote, and then you can draw a line through the other two corners, and that'll be the second asymptote. Okay, so let's do that now. So these are our asymptotes, and then our hyperbola. Okay, first of all, notice that the asymptotes go through the corners, but also through the origin. And then our hyperbola is going to go through each of the vertices, and it's going to asymptotically approach the asymptotes. That's why they're there. So we're going to draw in the hyperbola approaching each asymptote. Let's go ahead and do that. And that would be the graph of our hyperbola. So note that the hyperbola is only this branch and that branch. The solid lines are asymptotes. So they're just used to get the two branches of the hyperbola. Okay, let's see how we do a problem like this from beginning to end now. So find the vertices, foci, length of the transverse axis, asymptotes, and sketch the graph. And here's the equation we're given. So the first thing to do is put this in standard form, and you do that by dividing, or by getting 1 on the right-hand side. In this case, dividing both sides by 144. So when we do that, we're going to get x squared divided by 16, take away y squared over 9 is equal to 1. So I see that my a is equal to 4, right? So my a is equal to 4, and my b is equal to 3. So I'm looking at my vertices being positive, negative 4, and my foci. Now, the foci involves c, right? So recall that b squared, let's write this up here, b squared is equal to c squared take away a squared. So c squared is equal to a squared plus b squared. So c squared is equal to, in this case, 16 plus 9, or 25. So that means if c squared is 25, that means c is 5. So my foci have coordinates positive, negative 5, comma 0. So I found my vertices, I found my foci. The length of the transverse axis has length 2 times a, as we talked about. So let's write that down. So the transverse axis length 2a, so it's going to be 2 times 4. So the length is going to be 8. And the asymptotes are y equals positive, negative b over a times x. So it's going to be positive, negative, my b is 3, my a, with b being 3 and a being 4, we're looking at y equals positive or negative 3/4 x. Okay, so now we want to go ahead and graph the, sketch the graph of the hyperbola, and to do that we create our central box. So below y we had 3, right, or 9, so we're looking at 1, 2, 3, and then our vertices were at 4, so 1, 2, let me just get that 3, 4, then 1, 2, 3, 4, 1, 2, 3 on the y. So this is 4, 3, negative 4, negative 3. So our central box is going to look like that. Let's go ahead and draw that in now. So there's our central box. Let's go ahead and draw the asymptotes now in as well. So these would be the graphs of our asymptotes, and I labeled this asymptote y equals 3/4 x, and this asymptote has been labeled y equals negative 3/4 x, and they were obtained from this. And now let's go ahead and draw our hyperbola through the vertices approaching the asymptotes. So this will be one branch, and then the second branch will be over here. Let's draw those in now. So here's the graph of our hyperbola. Here's the right branch, right? And it goes through the one vertice here, and it approaches the asymptotes. Here's our other branch, and once again it's through the vertice approaching the asymptotes. And you can see that the asymptotes both go through the origin. Okay, so it turns out that you can also have your transverse axis not necessarily horizontal, you can have it vertical. Now if your transverse axis is vertical in the next example, we're going to see the hyperbola is going to look like that. So let's see what that looks like now. So this is a hyperbola with vertical transverse axis. Now here's the equation of it. Notice the difference. Instead of x squared over a squared, it's y squared over a squared, take away x squared over b squared. So in this case, you can clearly see that you have y asymptote, or y-intercepts, right? Because when x is 0, you clearly cross the y-axis, but you don't have x-intercepts because when y is 0, there's no solution to that equation. So it's very similar to what we had before, except the asymptotes are no longer b over a, they're a over bx. And then the foci, of course, are 0, positive, or negative c. So let's go ahead and draw in our central box and see what a graph of this might look like. So over here I have the graph of my hyperbola. So notice that I have my top branch here, and I have my lower branch, and they both cross at the vertices, right? Here's negative a, here's positive a. Notice that I also have my asymptotes, and notice that the equation, that these are once again lines, the equation of this asymptote is y equals a over b x, and the equation of this asymptote is y equals negative a over bx. So you might ask yourself, how do I know if I have a vertical transverse axis, like in this example, or a horizontal transverse axis? And the answer is it all depends upon what comes first, x or y. So if the y comes first, then you have y-intercepts, and then if the x comes first, you have x-intercepts. Okay, and then we're going to see in the next video how to graph conics that have been shifted. Until next time.